Okay, so we're still on our journey to try and use the Gram-Schmidt theorem. But we still need a little bit more background. So this is the next video to kind of give you some more background information on that we're going to need in order to employ the Gram-Schmidt theorem. So this one is going to be a discussion of expanding our vectors in an orthonormal basis. So basically, I mean, if we have a vector v and it's made up of these components, vi, and it's in some basis I, so we've defined v in terms of its own unique basis I. But then if I have a so then I always say, well, how am I going to find the projection of, say, one of those components in terms of the orthonormal basis that I've come up with? So to kind of, review, I is an orthonormal basis. And what I want to find is the projection of the j axis on the basis I. I want to find out what the j. So again, it's kind of like taking the dot product. You have a vector in the x, y, and the z direction, and you only want to find out what the x component is of that vector. So we have to project the x component, or we have to project that vector onto the x-axis. And that's all we're going to try and do right here. So the way we can do that in our vector spaces notation that we're using is we basically take the j-axis, and find the inner product with the vector v. So we're looking for the j component of v. And when I do that, I basically have my all my coefficients, and then I look at the inner product of j on the basis itself. On that, so again, this is kind of like taking the dot product. Now, if you remember from the previous video, that the inner product of I on j, so the inner product of two axes in an orthonormal basis, is the Kronecker delta, which is 1 if I is equal to j, and it's 0 if I is not equal to j, right here. So therefore, what I should get out of this whole thing is the j coefficient. So all other axes have now canceled out. There is no projection of an axis onto any other one. So basically, we're only looking at when j ends up falling on this projection on the j-axis. Therefore, we only get that coefficient right there. And so this inner product, j, so one particular axis on a vector, gives us that projection. It gives us the value of that right there. So therefore, I can now write my vector v as a sum over all the dimensions I times these coefficients times my basis I, but I can now rewrite this as the coefficients are just the projections of that axis on the original vector times the basis. And so the inner product here, this inner product of I projected onto v, is just a number. It's a coefficient, so I can move it anywhere I want. So a lot of times we like to rewrite this to make it look a little prettier, to have the cat and the bra organized this way. And so now what we have is basically rewritten this and gotten rid of the notation of the coefficient, and now we're only using notation of vectors, where this inner product is just the projection of that vector on the particular dimension I. I mean, if you want to think about it in terms of column vectors again, then you can say that this vector v is just the sum of vi times the basis, and my column vector v1, v2, dot, 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 down to vn is nothing more than that component times the unit vector for 1 plus the component 2 times 0, 1, basically the unit vector for the second dimension, all the way up to Vn, where we're now looking at the column vector for the n dimension, right there. Okay. And so now, if we go back and revisit a little bit the adjoint notation, so we're trying to get all the pieces together so we can use the Gram-Schmidt later on. And so if I do, if I go back and say I have a scalar, I have a number a multiplied by a vector v, and if I think about this in terms of columns, that's a times v1, a times v2, a times vn, like so. So the adjoint of this, if we think about taking the adjoint, that's turning this into a row vector, and I have to take the complex conjugate of both the a number, the a scalar, and the vector. So this becomes a complex conjugate v1 complex conjugate, a2 complex conjugate, v2 complex conjugate, dot, 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 an complex conjugate, vn complex conjugate, right there. And so really what we're doing here by taking the adjoint is creating this, turning that ket with a number multiplied to it into a bra with the complex conjugate of that number right here, right there. So if I think about it, I can apply the adjoint, or I can rewrite, I should say, the bra in terms of a sum of basis vectors. So if this is my original ket, where I take the sum of all the coefficients times the basis, and then I say, well, what is the bra going to look like? Well, I'm still going to take the sum. It's a sum of basis vectors. My basis vectors are now bras, not kets, and the coefficients, which may be complex, I have to take the complex conjugate of that. And so, therefore, the coefficient I found by taking the projection of the I dimension onto the vector v, the complex conjugate of this is basically switching it around, taking the bra of the vector v and the projection in the I dimension. So now what we have is we have rewritten these coefficients, which are defining our vector spaces, in terms of the inner product of the vector with the orthonormal basis, and we have it now for both. We have it for the regular components vi and the complex conjugate of those components. So to review, I can write the vector as the sum of I, so the ket of I and the bra of I, times the vector v. And I can write the bra as the sum of v and I and the bra of I. So now I have a definition for the bra and the ket of the vector space in terms of these orthonormal basis, and I don't have to worry about those coefficients yet. Eventually we'll have to calculate those coefficients if we want to get any real numbers and compare it to the real world. But right now we're just setting up the formalism so we have a common language to talk about the bras and the kets of a vector space.